Alright, we've got a positive integer, and it has a remainder of 2 when divided by 6, and it has a remainder of 3 when divided by 7. And the question is, find the sum of all such numbers between 1 and 1000. Jeez, seems like a hard problem, doesn't it? But sometimes you just sort of got to start diving in and working with what you're given, and sometimes you can make sense of it. So let's rewrite what we are given here. So we're given an integer, and when it's divided by 6, it has a remainder of 2. So what does that mean? It means that that integer is a multiple of 6 plus 2. Okay? So we have an integer that's a multiple of 6 plus 2, and it is also a multiple of 7 plus 3. Okay? Same integer, that's why I set them equal to each other. It's a multiple of 6, 6m, plus 2. Alright, it's some multiple. I don't know what the multiple is. And then it's also a multiple of 7. Okay, I used n in this case because it's not the same multiple as the multiple of 6. Alright, so it's some multiple of 7 plus 3. So it has to satisfy both of these criteria. Alright, so we can work with this equation, and so what I'm going to do is actually I'm going to subtract 2 from both sides. Alright, so I get 6m is equal to 7n plus 1. Now there's a little trick that you can use. This is actually a modular arithmetic problem, but I'm not going to introduce the notation for modular arithmetic. Alright, you can look it up if you're interested in learning more about modular arithmetic. But essentially what we can do is rewrite this side in terms of multiples of 6. Okay, so I know that there's one multiple of 6 in 7n, so it's 6n plus 1, or plus 1n, right? So 6n plus n is the same as 7n. So I'm not changing the changing anything other than the form it's written in. And then we have plus 1. And I know that I want both sides of this equation to be positive integers. Okay, it's the same number, and it's got to be a positive integer because that's what it says right here. It has to be a positive integer. So when we divide both sides by 6, I should get a positive integer. Okay. So we have a factor of 6 over here, and so we should be able to factor out a 6 on this side, on this right-hand side of the equation. Okay, if both of these numbers are positive integers. So what this means then is that n plus 1 must be divisible by 6. Okay, you see that? Divisible by 6. Okay, so n plus 1 has to be divisible by 6 because I know that 6n is divisible by 6, and when I divide both sides by 6 I should get an integer, right? And so if 6n is divisible by 6, then the only way that the whole thing can be divisible by 6 is if this is divisible by 6. Okay? So I know that n plus 1 has to be divisible by 6. So let's create a little table with some possibilities. I'm going to put n plus 1. These are our multiples of 6, and then n will just be 1 less. Okay, so let's write down some of the possibilities. So what I want is the first multiple of 6 that gives us a positive integer for 7n plus 3. Okay, I'm actually going to put 7n plus 3 here too, so I can compute what my integers are. Alright, so I want the first n plus 1, first multiple of 6 that gives me a positive integer for 7n plus 3. So if you look at 0, for example, 0 is technically a multiple of 6, but then n has to be minus 1, and then 7n plus 3 is negative, so that's not what we want. So our first multiple of 6 is 6, which gives us an n of 5, right? Which means that 7n plus 3 has to be 35 plus 3, which is 38. Alright? And our next multiple of 6 would be 12, which gives us an n of 11. and 77 plus 3 is 80. Okay, so now we have two integers that satisfy both of these criteria. They are, when divided by 6, they give a remainder of 2, and when divided by 7, they give a remainder of 3. Okay, so let's keep going, and because you wouldn't want to have to list out all of these numbers, but we can find a pattern. So we're looking for a pattern here. All right, so let's keep going and see if we can find a pattern. Our next multiple of 6 would be 18, which gives us an n of 17. And if we plug in 17 to 7n plus 3, we end up with 122. Let's go one more. Our next multiple of 6 is 24, and that gives us an n of 23. If we plug that into 7n plus 3, we get 164. All right. So you see, we actually have just, well, these are all our arithmetic sequences, right? Obviously 6, 12, 18, and 24. That's an arithmetic sequence with a difference of 6 between consecutive numbers. Here we have another arithmetic sequence, only it starts with 5, all right? But the difference between consecutive consecutive numbers is 6, so it's just an arithmetic sequence. And over here, if we look at the difference between consecutive numbers, it's 42, right? So you see the difference between consecutive numbers over here is 42. So here's another arithmetic sequence, okay? So we can actually, what we want to do is find out what's the what we'd like to know is what's the last number before we get to 1,000 that satisfies this criteria, okay? Because then if I've got a video on how to sum arithmetic sequences, and it's pretty neat trick. So if you haven't seen that, you should watch that. But we have a sequence of numbers that starts with 38, and every consecutive number just adds a multiple of 42. Okay, so the first one has 0 multiples of 42. The second one has 1. Okay, so it's essentially the ordinal value minus 1. Okay, I'm going to call it j in this case. I usually use n, but I already used n for something else, so I don't want to get them confused. So I'm going to add an ordinal value for each one of these numbers as well. But when I mean my ordinal value, it's just the position of each one. So this is the first term, this is the second term, third term, fourth term. Okay, it's the ordinal value of the term if we have these numbers ordered from lowest to highest. Okay. All right, so we have this arithmetic sequence that looks like 38 plus 42 times essentially 38 plus a multiple of 42. All right. And we want that to be less than 1,000. Okay. So let's take a look at that. Let's subtract 38 from both sides. And we get 42 times j minus 1 is less than what? Oops, hang on. Got ahead of myself here. All right, so 10 minus 8 is 2, and 9, that's 6, 962. All right, so j minus 1 is less than whatever 962 divided by 42. All right, let's divide 42 into 962. All right, so goes twice. That's 84. And we have 12, 122. If I multiply this by 3, I get 126. That's too big, so this has got to be 2 again. All right, 84. I subtract that. I get 38. Interesting. All right. All right, so j minus 1 has to be less than 22. So j has to be less than 23. All right. So I'm guessing our last one has an ordinal value of 23. All right. So let's see what we get if we put in 23. So 23. So 23 minus 1 is 22. So 42 times 22 is what? That's so it's 84, 84, 4, 12, 924, and then we have to add 38 to it. And that's going to bring us back to this 962, right? So the 23rd value is going to be 962. All right. So we have an arithmetic sequence that starts with 38 and increases by 42 each time up to 962. And if we add one more 42 to that you can see that we go over 1,000. So that's as far as we can go. All right, so let's sum this arithmetic sequence. All right, so how do we sum an arithmetic sequence? We take the first number, 38, plus the last number, 962, okay, times the number of numbers in this list. Well, I listed the ordinal number here, so there's 23 terms. All right, so we have 23 numbers, and divide that by 2, right? So what does that end up giving us? That ends up giving us, let's see, I ended up with 2,300 over 2, and that's just because you can see 962 plus 38 gives us 1,000, right? So 1,000 times 23 divided by 2, and I can divide that by 2, and I'll get 11500. All right. So this is our sum. I'm going to use the Greek letter sigma. So our sum is equal to the first plus the last times the number of numbers divided by 2. Okay, so, phew. Well, we didn't have to add 38 plus 80 and then take that and add 122 and then add 164. We can use this nice little formula. And so the sum of the numbers that meet this criteria, that are have a remainder of 2 when divided by 6 and a remainder of 3 when divided by 7, between 1 and 1,000 is 11,500.